let me start. I need to hide. Oh no, it's okay there. Here. Okay. Let me start just introducing the subject robotics, because sometimes it's misunderstanding. Because when we think popular in robotics, we always think about human robots or animal-like robots or autonomous vehicles and autonomous device, and properly it's not robotics itself. So let's just start to talk about robotics and show some concepts, and after that we can talk about the projects I'm working with. Okay, so robotics is an interdisciplinary branch of engineering and science that includes mechanical engineering, electronics engineering, information engineering, computer science, and others. Robotics deal with design, construction, operation, and use of robots, as well as computer system for their control, sensory feedback, and information processing. So for the industrial point of view, robotics is more like this screen, this photo of the left side. It's more like arm manipulators or arm robots, because they can be programmed to perform different kind of applications. So I always ask, what is a robot? So sometimes we think that a 3D printing is a robot, but technically it's not a robot itself. So using the concept from Craig, the book Robotics, if a mechanical device can be programmed to carry out different kind of applications, it is probably a robot. So this mechatronic device here, it can be programmed to paint, to pick and place, to weld. So it can be a robot. This device here as well, it can be programmed to talk with humans. It can be programmed to take something and took to anyone. So it always can be, it also can be called robot. But 3D printing just can be programmed to 3D print. So we say that a 3D printer is a mechatronic device, not a robot itself. Also, we have here another kind of 3D printing, so it just can be programmed to print. And this is a CNC, computer numerical controller, machining this material to form some kind of device. And also it just can be programmed to do this kind of thing. It's not, it can't be programmed to, I don't know, to pick and place or to painting or something like that. So because of that, we call this kind of thing as robots and this thing as mechatronic device. But always we saw that robots is different kind of things, like that robot, the cleaning robot that clean your house. It's not a robot itself, because it just can be programmed to clean the house. But sometimes we can see that in different contexts. So here we have a manipulator or a robot, and here we have one. Let me just stop it. So we have here a arm robot, and here we have a human arm. So these robots are built, are conceived to reproduce the number of joints we have in our arm. disregarding the hand, because here in the arm we have 7 degrees of freedom. So we have 7 independent movements to perform with our arm. We have 3 movements in the shoulder, this, and this, 3 movements, 1 movement in the elbow, 1 in the forearm, pronation, supination, and 2 here in our wrist. So this robots here can have also 5, 6, or 7 degrees of freedom, so that they can perform like human arms. Okay, so each degree of freedom have an actuator that is responsible to move that joint. And here we have how one of these actuators works. Is basically a motor, an electrical motor, coupled to reducer to reduce the velocity of the joint and improve the torque, the force. Like a bicycle when you change the steps. And internal, it has encoder to measure the angle of the joint. So with that, we can know all the angles of each joint, and with that we can know the position of the arm in time. Okay, just knowing the velocity of each joint, we can know the position of the arm. So with these base concepts, we can go further in our applications. So prosthesis, what are prosthesis? So a prosthesis is an artificial device that replace a missing body part. So if you lost a body part, you can replace it with a prosthesis, okay? Which may be lost or by trauma, disease, something like that. Prostheses are intended to restore the normal function of a missing body part. So why I'm talking about prostheses is because I work with that, and it's important to know what is a prosthesis, what is an exoskeleton, what is an orthosis. That's the next slide. And an exoskeleton or an orthosis is a different device. It's not used to replace your body part that you lost for what else? It's used to support your body, a body part, or just to improve or improve the power of that body part. So we have here an exoskeleton, a full body exoskeleton. This is the whole Japanese exoskeleton. It have actuators in the legs and also in the arms, so that this exoskeleton is used to improve the power of this human. So you can see that it's carrying a heavy load with the help of this exoskeleton. And an orthosis is more like a passive device, or a device that can help you to fix your joint in a fixed position, or just help you to support the loads of that joint. But an exoskeleton make the movement for you, help you to make the movement, okay? So we also have passive device, semi-active device, and active device. It's important to know. So an active device is that one that make the movement for you. So it introduces power to the movement and make movements for you. Like if you have a prosthesis, a knee prosthesis that make movements for you, it's an active device. This active device can dampen the movement and provide energy. to that movement and have high energy consumption. So the passive device do not provide damping control and not provide energy. It's just a single joint without microprocessing. In a semi-active device, it's used to control the damping and also provide, but not provide energy. So it don't have, it have a low energy consumption. So for our purpose here, I'm working with active device. So the intention is provide the energy for the user when the user can't perform the movement. This in a prosthesis. So if someone lost the leg, we are working in lower limb prosthesis that can provide the energy for the user. And if the user lost the movement of arm, for example, we are working in orthosis and exoskeleton to improve the movement of the user. So here we have different kind of exoskeletons, and all these ones are active device, and they can be portable ones like this. You just wear it and go with a backpack and batteries, and you can perform your movement. So this is the purpose of these two ones here. This one, it's fixed in a workbench that can be used in clinicians and hospitals to rehabilitate the movement of the user. So here we see here an exoskeleton used to rehabilitate the movement of the arm of stroke survivors. So, and this one here is an exoskeleton. It's a commercial available exoskeleton of Locomat, Hokoma. It's a well-known company about robotics for medicine, and the Locomat provide movements for the lower limbs of people with some kind of impairment, and the exoskeleton is assembled over a treadmill. So we have here a treadmill that it's running, and the user follow the movement of the treadmill with the help of the exoskeleton. So I had the opportunity to wear this one of this in Harvard Medical School, and it's amazing. They perform different kind of movements, fast, slow, and provide different kind of assistance. If you just want to assist 50% of the movement, it's just 50% of the movement or 100% of the movement, so that it's very useful for rehabilitation, lower limb rehabilitation. Okay, but the problem is this: the user is always stuck, and the legs walk, but the user is don't move, stationary, and the legs move. Okay, so there is some research that say for rehabilitate lower limb movements, it's necessary to challenge the balance control of the user. So when you are stationary, just your legs move, you are not challenging the user balance control. So that it's better if you have a system that can walk over the ground. So because of that, this is the project where that I work with in the US. This is a lower limb exoskeleton for overground guide training. So the user wear this exoskeleton and walk over the ground, and the exoskeleton can help the user to find a physiological gait. So the idea here is talk just a little bit about this project, and next we can talk about another project. So we have here an exoskeleton. This exoskeleton have 6 degrees of freedom, 3 for each leg. So we have in each leg assistance in the ankle joint, assistance in the knee joint, and assistance on the hip joint, okay? And the another leg, the same. So here we have this exoskeleton wear and myself, and the control system is placed over a ceiling support to reduce the weight of the system, so that I don't need to bear all the batteries and this kind of thing. The system get really light, and just weight about 7 kilos, all the system that I'm wearing here. And the human machine control is over here. So the clinician can set the number of steps and this kind of thing, and the exoskeleton works properly. So, but there is just a small and a big problem in the same time, because the exoskeleton is very, very light. So the weight is not a problem, but it's very hard to move the joints when the exoskeleton is off, because the transmission used in the actuators is so high. It's like try to move your bicycle when you can set the how can I say that, the transmission height there, you can set to a light and to a hard movement. So you know, when you try to drive the bike with when it's set to a fast velocity, it's hard to make the movement. It's the same principle here. So we have here a fixed transmission height, and it's very hard to move the joints of the exoskeleton. So it makes the movement hard to be done for people with some kind of impairment. So I went to the US. I was invited to work in this exoskeleton to make it transparent for the user, so that the user do not feel the exoskeleton as when it is turned off. So this first video, where is it? This first video, you can see me trying to move the joints. So I'm making a lot of, it's a hard movement. I make a lot of effort to move that joints. It's hard. So the second video, can you see? It's hard. So the second video is the system working with the control system that I work with, and I improve it there. So it's a way transparent. It's a way easier to perform these movements. You can't see, you can't hear the sound, but now the motors are working and help me make the movement. The exoskeleton is trying to understand what I'm trying to do and performing the movement, okay? It's just a way to make the exoskeleton more transparent, so that I can walk more easily with this exoskeleton. Yeah, that is. And this is another control mode that I programmed with there to help the user walk with the exoskeleton. So the exoskeleton here is walking for me. I'm just following the movement of this exoskeleton, because I can walk properly. But a user that can't walk very well can have the gait improved with this control system. So the system is walking and help me to walk for several steps.
So Rafael, you're not moving your left leg in that video, right?
Sorry,
the system is moving it.
Say it again, please.
You're not moving your left leg in that video, right? The system is moving it for you.
Exactly. The system is moving my leg for me. It's helping me to move the leg. Yeah, exactly. It's trying to, there is some sensors placed in the exoskeleton. Here, they have a potentiometer to measure the angle of the joint. They have strain gauge to measure the interaction force with me and the exoskeleton, and pressure sensors and the insoles, so that the exoskeletons knows when I'm with the foot over the ground, and when I'm with my foot flying. So it also have, yeah, this is the sensors, and with the sensors we can program a good way of help the user walk again. So this is the first experiments we did, and we are working. We keep working in this project, and we just have a paper accept for publication in transactions on medical robots and bionics in January, and I'm working in another research with this exoskeleton. So it's a nice project, and I really love it. The opportunity to work with it. It was blow-minding for me. I didn't have the opportunity here to work with some system like that, so that it was really important to improve my understanding about it. So the second project, it was my PhD. I developed a knee prosthesis, an active knee prosthesis. So we just have one active knee prosthesis in the market today, just one, the power knee of Osur. It's so we also have a big market to feed with active knee prosthesis. These active knee prosthesis can perform the movement for the amputee. So in this project, I used this smart material called magnetoreological fluid. So sorry for that, it's in Portuguese here. I just forgot to translate, sorry. But this is how the magnetoreological fluid works. When when there is a magnet field flowing through the fluid start to form these chains of particles. So sorry, the fluid is a colloid material that is composed by magnetizable particles and oil. And when magnetic field pass through the fluid, it starts to behave like a solid, like a semi-solid material. So you can see here, the system starts to behave like a solid, is not like a fluid. So with this behavior, we can construct different kind of device. So brakes, dampers, and clutches. And with this material, we built this concept of knee prosthesis. So basically, we have here a motor and a reducer to produce the movement for the user here. And we have here a clutch that use magnetobiological fluid, and a brake that also use magnetobiological fluid. So we have a magnetobiological clutch and a magnetobiological brake. With this configuration here, the system can work like a motor, a brake, and a clutch, and have multi-operation modes. So we build a operational system that try to use the better of each subsystem that I said, and with this configuration, we can have here in this graph a reduction of energy consumption about 40%. So the idea behind this project is to reduce the energy consumption of knee prostheses, because these knee prostheses spend a lot of energy and they need big batteries, and the system got really heavyweight. So the idea is reduce the energy consumption and make the system more light. And here we performed these experiments, and it was published in Journal of Intelligent Material and System and Structures in January of this year. And here we have the energy consumption of each system for the one guide cycle. So we can see here, the blue one here, 0.7 joules. The brake just spends 0.7 joules. Instead, the motor is responsible of spend 13 joules. So that's why we try to use the motor in the moments that it's necessary, and in other moments we can just use the brake, because sometimes when we are walking, we just use the knee as brake, not as motor. So this is the idea, reduce the energy consumption of the system. So this is a video of how the system works. It's also in Portuguese, sorry for that, but here we have the internal housing that house the motor and the reducer. And over the motor, we have the brakes. The brake, just one. And over the reducer, we have the clutch, not here. This is just bearings to improve the movement and reduce friction. Here we have the clutch. And the external housing and the closing, the closed parts. So how it works. When active movements is required, the motor is activated. The reducer and the clutch. And the knee perform the movement for the user. When just braking is required, just the magnetobiological brake works. So the magnetobiological brake spends a way less energy than another system. So we can works with this two operation to reduce the energy consumption of the system. So I also have here, let me show you, I don't know if you can see or not, but I also have here. Can you see my screen? I'm showing the 3D model.
We can see the screen, but it's not showing.
Let me try to share. Let me try to share the another. Stop you sharing. Can I stop sharing? Just.
Sure.
Okay. Now can you see my?
Yes.
Yes.
So here we have the prosthesis, all the prosthesis. So here we have a foot, and here is the thigh of the user. So here we have all the systems inside, and so this is the 3D model, and with this 3D model we can understand how the pieces are assembled, and it's very, very important. Before a physical prototype, you have a digital prototype. So in 3D printing, you need something like that to print. So, but here we have many pieces assembled to make the system. So some parts of the systems are printed in 3D printers. So and before build the system, you can also print all of it and test if it's assembled well or not. And it's easier to work with mechatronics and design this kind of device when you have a 3D model, and when you have a 3D printed model like that. So this is the motor, reducer, magnetoheliological clutch, and magnetoheliological brake. Okay. So, and let me stop again and share this. Opa. So, and to finish my presentation, we also have another project that is a brain-machine interface arm exoskeleton that is starting. We just start this project with University of São Paulo, and the idea behind that is to build a system to help a stroke survivor rehabilitate movement of feeding, like take a glass of water and bring to the mouth and take it. So the first step is just build the system. Virtual reality will help the user to train how to operate the system, to have a visual feedback, and the system will be operated by a physician with external device, like a tablet or something like that. And the second step is introduce a brain-machine interface to operate the system and help the user to get something. The brain-machine interface is a direct pathway between your brain and an external device. So the idea is try to operate the system with the thoughts of the user. But if the user have some kind of issue on the nervous system, it's not easy to use a brain-machine interface to operate it. So that we will have some challenge to perform that, but we are confident that we can do that. So it's just a beginning, and part of it was the first prototype of this orthosis is it was printed, it was 3D printed, and here there is a video. It's helped me to make just flexion and extension of my elbow. This operate with cable actuators, so that we don't need to put motors and reducers here, so that we can make a system very, very light. It's just about a half kilo. Instead, if we had motors here, the system would be 2 or 3 kilograms. So we just have a half kilogram device. And we use cables to drive the joints, and the motors are placed in the backpack of the user. So, and this is the video of the movement of pronation and supination, how we'll perform the movement of pronation and supination. This is the actuator. It also operates with cables. This first design was presented in a conference, and that's it. I think that's my presentation. So thank you for the opportunity, and I'm open for questions, and I hope you have enjoyed it. So thank you.